Okay, and let's start our midterm review today. Okay, any questions so far? So midterm will be about what we have taught, what we have been taught so far, and so it's mostly quantum mechanics with a bit of quantum circuit. Okay, so yeah, this review file is basically a condensed version of all the previous lecture notes, and yeah, so we'll go through things that. As a small review of go through like the important points that we've taught. Okay. So first of all, I want to emphasize on things silent notation and the things that we should just memorize. Okay. And first of all, polymatrices, we have seen them quite a bit in all sorts of calculation. And once again, polymatrices are those three matrices. And they are denoted by x, y, z, or sigma x, sigma y, sigma z. And x is 0, 1, 1, 0 matrix, y is 0, minus I, 0 matrix, and z is 1, 0, 0, minus 1 matrix. And they are quite special. They are all unitary matrices, and they are all Hermitian matrices. And we also know the eigenvectors of the polymatrices a little bit. So we know the eigenvector of this matrix, Z matrices, is just a computational basis state 0 and 1. And so Zx on 0 will become 0, and Zx on 1 will give you a minus 1 phase and 1. And and we also know the I guess I didn't write here. We also know the eigenvector of the X matrix. This is plus day and minus day. Okay. And plus day has plus 1 eigenvalue, and minus day has minus 1 eigenvalue. And we should write down the plus state and the minus state here. The plus state is this normalized 0 plus 1. So plus state equal to 1 over square root 2, 0 plus 1. And if you return in matrix notation, it's 1 over square root 2 of 1, 1. And the minus state is the 1 over square root 2 over 0 minus 1. So it's 1 over square root 2 is 1 minus 1 state. Okay. And yeah, here we also have the Dirac notation, Dirac function. We have this delta jk notation, mean equal to 1 if j equal to k equals 0, if j not equal to k. Okay. And but let's go back to matrices. So we have these x, y, z matrices, and also one of them another unitary and Hermitian matrix that's very nice is this Hadamard matrix, 1 over square root 2, 1, 1, 1 minus 1. And it's very good because it is transformed between basically transformed between Hadamard x and Hadamard z. So we know that. It transforms between poly x and poly z. So we know that you can see the effect here. So we know you have a Hadamard matrix acting on the z eigenvector, become the corresponding x eigenvector. And also, if you we know that the Hadamard square equal to identity, and Hadamard this plus state will go back to the minus 0, and Hadamard minus state will go back to, it should be 0 here, and there should be 1 here. Okay, so Hadamard matrix acting on 0, 1 become the plus minus state. And Hadamard matrix acting on plus minus state go back to 0, 1, and it's consistent with Hadamard square equal identity. And also another thing is like you can act on the matrix itself. We know that Hadamard x, Hadamard equal to z, and Hadamard z, Hadamard equal to x. Okay, so those are polymatrices and the Hadamard matrix. You can see Hadamard kind of Hadamard switching between x and z in these two different expressions. You can either conjugate your x to become z, conjugate z to become x, or you can just have Hadamard acting on the eigenvector and change it from z eigenvector to x eigenvector with the same eigenvalue. Okay, and then we also have a computational basis state. And so 0, this is the most standard basis state we have. And if you write down in vector form, it's just you have 1 somewhere and a 0 somewhere. So 1 0 0 0 0 or 0 1 0 0 0 0 or 0 0 0 0 1 state. And then we have a bit of a notation issue. So this is a standard computer science dilemma of whether you counting from 0 or you count from 1. So here we count from 0. So this first state actually says actually is named 0, and the second state named 1, and we have n state here, and so we count from 0 to n minus 1. So we think if you have bigger dimensional, excuse me, you have a bigger dimensional vector space, then the computational basis states are those simplest possible vectors, and we give a notation as 0 to n minus 1. And yeah, this will correspond to log base 2n qubit state. Okay. And then next we have our gates. So we have those matrices, and those matrices, they also correspond to single qubit gates. Okay, so you can add your x, y, z, and sigma on single qubit. And then we have some two or more qubit gates that we should memorize. And so first is control unitary notation. We have that unitary control. If we want to control on first qubit, act on the second qubit with unitary u, then we write this control unitary notation. Okay. And so what happens is you have computational state. So so if you have computational base state A here, and then the second qubit will get acted by u to the A, means that A equal to 0, you don't act this u, A equal to 1, you have a u side on whatever input side. Okay. And so this is a general rotation for control unitary. Then we have some special control unitary that we use a lot. And I guess the most famous one is this C-NOT gate. Okay, so this is control on first qubit, apply the NOT gate on the second qubit. And we also know that NOT gate is also just the S gate, because the S gate flip between 0 and 1. Okay. Okay. So we have this control NOT gate, and so if we write this as a general control unitary notation, it will be this control. So the control is written as a solid dot, and the unitary as this NOT gate, which is X gate. And but we also have a special notation where control NOT gate is just written as this. So you have a solid dot as your control qubit, and then target qubit is this. We return as this circle. Yeah. So this is control NOT, and also control NOT in terms of its action on computational basis, we have a very simple algebraic notation. So if the input is AB for AB computational basis state, then the output will be first qubit still states A, and the second qubit will be A, X, or B. So this circle plus means XOR means addition mod 2. Yeah. So AB to A and A plus B. A XOR B. And then the other important 2-qubit gate to be remembered is this control Z gate. So yeah, so it's a control first qubit and 18Z on the second qubit. But if you but you can easily check that this 2-qubit gate is symmetric between first qubit and second qubit. Means that if you control on second qubit and apply Z on the first qubit, this is the same gate. And so we have this funny notation for control Z, which is just you have both you have control on both sides. Okay, so you have put solid dot, means that you control you put solid dot on both sides, and this actually means control Z between those two lines. And control Z being symmetric can be easily checked on the notation here. Okay. And I guess can be easily checked on its action on the computational basis state, and or you can just read from this matrix of control Z. So you see that if you have AB as input, then the output will be, okay, maybe in this notation it's more clear. So AB as input, then the output will be still AB, but with a phase of -1 to the AB, A times B. So here is AB means A times B and A equal to 1 if only if both A and B equal to 1. Okay, so you see that this result is very symmetric between A and B. Yeah. And so that's control Z gate. And next we have swap gate. It's written as this. Excuse me. So once again, it's a 2-qubit gate. So we connect them and we write a cross on both of the qubit. And what it do is swap whatever state you have on first qubit with whatever state on the second qubit. So if you have AB as input, the output will be BA. Okay, and even for general pure state, it's also true. So if you have psi-phi, as we said previously, so if you have psi-phi, then after swap gate, it will become phi psi. Okay, and here is the construction of swap gate that you can do by C0. So if you have those 3 NOT, it will become swap gate. And then next we have Toffoli gate. We haven't talked about how to control it, but this is an important gate to know. So Toffoli gate is a control NOT gate. Okay. So this is apply the NOT gate on the last qubit if only if both first qubit and second qubit is 1. So if your input is ABC, the output of the control qubit is still say AB, and the C got plus AB. So C got plus something if only if A and B both equal to 1. Okay, and here I guess actually really say C or plus AB. Okay, we are being a little lazy. Okay, and so that's our first 3 qubit gate. That's a Toffoli gate, control X, and we can also have control Z gate. And so just like control Z, it also has this funny notation where you put this control register on all 3 qubits. Okay, so this is control Z, and then you can just check the form of this output that is also symmetric between A, B, C. That's why we can write it this way. So control Z, control on first both qubit 1 and qubit 2 equal to 1, then you apply the Z gate on the third qubit. And so basically this gives you a -1 phase only when both A, B, C equal to 1. But phase you can put everywhere, so this is really symmetric over the 3 qubits. Okay. And yeah, so those are basic gates and notation to be remembered. Any questions so far? If not, then let's go to more review on materials. Okay, so next we review Dirac notation, and we should really be very familiar with the Dirac notation, but here we just go over them again. So we write this K notation to mean a column vector. Okay, so so we have this straight line, and angle means and whatever, and for symbol inside this means column vector. So for example, we can have a column vector 1I, so this is a 1 qubit state. Okay. And then we have this broad notation, so angle and straight line, this means a row vector. And but here we introduce more notation here. And so we can have a column vector and its associated row vector, which is its dual. So we have the same notation inside, and we mean those 2 vectors are dual to each other. And this dual is formalized by this dagger notation. Okay, so we have this complex conjugate. It means that you do dual on your vector, and well. And when you do dual, basically you do what you do is you do transpose and complex conjugation. So dual, you do this Dagger operation, and this means transpose plus conjugate transpose. So what happens is you flip this one I in a column to one I in a row, and then you do complex conjugation, so this I become minus I. Okay. So important thing happen is I become minus I. This is a dual operation. You do Dagger. Okay. And then the inner product between two vectors. So some AV and BW will be you put a dual on the first vector and just do matrix multiplication between those two. So you do dual on AV, then A become A star, and you dual V, and this V become this V cat become V bra, and so you can multiply the scalar together to A star B, and this VW you multiply, you can do matrix multiplication together. Okay. And then we also have outer product, which is you just do matrix multiplication. So you have psi cat times psi bra, then this is basically a projector on two sides, and you will become this matrix. So psi cat, psi bra, and you do matrix multiplication. So 1 times 1i becomes 1i, and the minus I times this 1i become minus I and 1. Okay, so those are basic Dirac notation. Yeah. I guess we should write one more example. So if you have this psi times phi, then you just have, or psi times psi, then you just have matrix multiplication, and you have 1 minus I times 1i, and this is 1 plus 1 equal to 2, and this is also equal to the known square of your psi. Okay. Matrix inner product with yourself is its known square. Yeah. Okay, and so those are the basic Dirac notation. Then in terms of linear algebra, we have the harder thing. Okay, so far this is just a complex linear algebra with complex number, and in terms of linear algebra, a special thing we only introduce in quantum mechanics is this tensor product. Okay, and tensor product we define as the product of matrices. Okay, so we say basically what we do is we have a different slot for matrices. Okay, so say we have some matrices A, B, C, D with some dimension, then we can always define this tensor product, okay, to become much larger matrices. And then the tensor product will satisfy those rules where A tensor B, okay, and where it's where you multiply the tensor product with a scalar, then you can you can put your scalar everywhere, and then tensor product is linear. It has a distributed law, so you have A plus B tensor C, then you have A tensor C and B tensor C, and A tensor B plus C equal to A tensor B plus A tensor C. Okay, and so those are the basic rules you think that will happen for a product, and then there are more special rules. So if you put a dagger on your tensor product, then actually the ordering doesn't change. Okay, so A tensor B, if you want to dagger this thing, is actually A dagger tensor B dagger, and in particular this means that you have some VW, which means V tensor W, and you put it dual, so you want to see it's a dual vector, then it's actually V bra tensor W bra. It's not W bra tensor V bra. Okay, and then I guess the most used rule of tensor product is that if you have something tensor product multiply another thing tensor product, then so we'll try to do matrix multiplication, then actually each slot multiply with each other. So it's A tensor B times C tensor D. you just have A times C and tensor B times D. And so obviously for this rule to hold, you need to have A times C defined and B times D defined. So you need to have some matching between the dimension and in the middle. Okay. But yeah, so in general, tensor product, if you have you can really have a tensor product of any matrix. So if A is N1 by N2 matrix, let's say, if you have A as N1 by N1 matrix and B is N2 by N2 matrix, then we really have A tensor B. We can think this as N1, N2 by N1, N2 matrix. Okay, so that's the tensor product. And so we see an example of doing this calculation with tensor product. So say we have the tensor product of 0, 0 plus the tensor product of 1, 1. And then multiply with this tensor product of this projector of plus tensor identity matrix. Okay, so basically we think what happened with this 1 over square root 2, 0, 0 plus 1, 1 multiplied by this projector of plus plus on first qubit and the tensor do nothing on second qubit. And then by the distributed law of tensor product, then this is this plus plus tensor identity acting multiplied with this 0, 0 plus this plus plus tensor identity acting on 1, 1. Okay. And so plus plus tensor identity acting on 0, 0, and then we use this. Then this is plus. So if we write it out, will be plus plus 0, then tensor identity on 0, and then we know this is so plus and 0 inner product is 1 over square root 2, and then this become 1 over square root 2, and so this is just a number. So the first register is left with a plus, and tensor identity acting on 0 is just 0. Okay, so you see the first so the first component is this plus tensor 0. And then you also have all the leftover numbers, so it has this 1 over square root 2 as z. Okay, so we start with this 1 over square root 2 as z multiplying outside, and so we can just have the 1 over square root 2 multiplied with this 1 over square root 2 to get 1 over 2 here. And so similarly, then the second term, we have plus plus, we have plus plus tensor identity. We have a plus plus tensor identity acting on 1, 1, and here plus plus tensor identity acting on 1, 1. So we just have plus plus multiplying on 1, then tensor identity acting on 1, and this once again plus. The inner product between plus and 1 is 1 over square root 2, and so this is 1 over square root 2 plus, and the tensor identity acting on 1 is just 1 again. Okay, so the first component become plus and 0, second component become plus and 1, so you can have this thing, and then you can group things together once again by the distributed rule, because by distributed rule this is 1 over square root 2 plus and times 1 over square root 2 of 0 plus 1. Okay, so we are grouping the second register together because the first register is the same, and then we know 1 over square root 2 0 plus 1 is plus that, so it's 1 over square root 2 plus tensor plus. Okay, any question on this calculation? Not? Then let's talk about measurement. Okay, and we talk about there are 3 different measurement formulation, and but it's kind of like actually 4 of them. Okay, so first one is a measurement we actually use in our second model. Is measurement in computational basis. Okay, And then we have the three measurement model is measurement against the orthonormal basis. Some orthonormal basis we have the basis vectors as vi here, or you can measure some Hermitian operator A, or you can have a generalized measurement described by those matrices Mi. Okay? And measurement in also against the orthonormal basis is simple. So if you measure some state with some orthonormal basis, then you will have probability to get some outcome I associated with this index I here. Okay? So probability of getting ith outcome is just the amplitude of your vector on the ith coordinate in this basis. Okay, and so that's just this amplitude square. So the probability is this amplitude square, which is the inner product between vi and the psi squared. Absolute value squared. Okay, and when you get the ith outcome, then since it's very simple, your state just become whatever basis measure basis vector you measure. Okay, so if the outcome I happen, then the state of the system become vi. Okay, so this is against orthonormal basis. And so say if vi is your computational basis, then it is just basis 0, 1, or longer strings you have more qubits. So if you measure 1 qubit in computational basis, then this is 0 and 1, and you will get your state will get 0 and 1 with some probability. Okay, and then we have measuring a Hermitian operator. Then measuring a Hermitian operator is quite kind of like measuring in the orthonormal basis. So we start with realizing that the Hermitian matrix can be diagonalized in this way. So summation I, lambda I, and vi cat, vi broad. So those lambda I are eigenvectors, and because A is Hermitian, the eigenvalues are real, and those vi's are orthonormal vectors. Okay? And orthonormal eigenvectors. Okay? And so measuring Hermitian matrix is a lot like measuring in orthonormal basis of those eigenvectors, but there are two major differences. And the first one is basically how we label the outcome. Okay? So previously we just say we get ith outcome, but here the outcome are labeled by the eigenvalues. So when you get I, you don't say you get ith outcome. You say we get we say we measure outcome. The outcome is lambda I. Okay? And the other thing is because the outcomes are lambda I, then some of the lambda I can be the same. Okay? And when the lambda I are the same, you really cannot have a unique vi here, because you can have vi1 and vi2 all have the same lambda I, and the vi1 and vi2 can have some freedom in the choice. Okay? So this is what happened. So this is what we call degeneracy. So if some eigenvalues are the same, and then you really cannot distinguish the eigenvector of the same eigenvalue. Okay? And so instead we need to have this projector onto eigenspace. Okay? So we define the projector Pm is that so if some eigenvalues are equal to m, then it's a projection onto all those space spanned by those eigenvectors. Okay? So Pi is sorry, it should not be Pi, it should be Pm. Okay? So Pm is the projector onto the eigenspace of A with eigenvalue m. Okay, and so instead of writing A as a summation lambda I projector onto eigenvalue ei, vi, we have A equals summation m of different eigenvalues, and then this Pm projector onto eigenspace of associated projector onto eigenspaces associated with eigenvalue m. Okay, and with this new decomposition of A, that's taking care of our degeneracy, A equals summation n Pm, then we can have the outcome probability of getting n and the post-measurement state of n. Okay, and so hint is basically the state become P is Pn on site, and the probability of getting outcome m is Pn psi non-squared. Okay, and it can be also writing as this form. And the post-measurement state is basically Pm psi normalized, so Pn psi divided by this norm. Okay, so So the post-measure state is basically Pn side. So the probability is this thing amplitude, the amplitude square of this thing, and then the post-measure state is this thing normalized. Yeah. And then next thing about special nice thing about measuring Hermitian operator is you can think about its expected value. So you have different outcome has different probability. So different outcome n has different probability Pm, and you can think about the expected value of all those outcome, and that should be summation over m different Pm, and that can be written in this nice form, which is a sandwich ring with this side. Okay. And then finally we have generalized measurement. Generalized measurement is m. This is just a set of matrices satisfying this relationship summation I and my dagger and my equal to identity. And then kind of similar to this Hermitian operator. So outcome I is kind of similar to the Hermitian operator case. If you want to know the outcome probability and the outcome state, basically you calculate this mi side. Okay, and so the outcome probability of getting I is this mi side squared. Here we have typo again. Excuse me. And when outcome I happen, then the state collects into mi side normalized. Okay, so that's measurement, and then we talk about a little more about polys. Okay. So the polys X, Y, Z, they have a nice property. So first one is that each pair of the anti-commute means that you have X, Y, with this means matrix multiplication. So X matrix multiplied Y matrix equal to negative of Y matrix multiplied X matrix. And all of them are Hermitian and unitary, and I give you that. I guess a little more. They are Hermitian unitary, and their eigenvalues are just 1 and minus 1. Of them has 1 minus 1 as eigenvalue. And also we have this kind of polys in different direction. We know that if you have a unit vector n inner product with if you have this unit vector n and a kind of inner product with this sigma vector, means that you have nx times sigma x plus ny times sigma y times nz. Here we have typo again, sorry. Times nz sigma z. Then then this is like a polymatrix in sigma direction. Okay. This is what we return in the block sphere. This is what we write in the block sphere. So we say this is like in 1 qubit we have this n hat, and then this n hat dot sigma will be like a poly in this kind of n hat direction, and there is some connection to block sphere. And in particular, we say this is like a poly because it has eigenvalue 1 and minus 1. Okay. And this will give you nice properties like n hat n dot sigma square equal to 1, like it's square to identity matrix, or is trace equal to 0. Okay. And for the last 10 to 15 minutes, we want to talk about density operator. Okay. Because we need to be a little faster. Okay. So density operator, this is what we use to represent the ensemble of a pure state, which means that if we have some classical probability mixture of states, okay, then we'll get the density operator. So we have some states, we should say psi I here, okay, excuse me, one typo. So we have some state psi with probability psi, then this ensemble, we call the ensemble pure state, and so just some classical probability pi, and mixing those state psi, and then we can have we can write down the density operator as the summation I pi and psi k the psi bra, and we say that we have proved that this density operator actually has all the property, all the quantum property you have with this ensemble of pure state. Okay. And maybe for example, so we have probability 1/2 having a state 0, and probability 1/2 having a state k plus, then we can write down the matrix rho as 1/2 0 0 plus 1/2 plus plus, and the write down matrix is this matrix. And this matrix will tell you all the property that can happen to this quantum system. And in particular, then you can evolve this density matrix. So if you evolve it with some unitary, then rho will become U regular, U rho U dagger. And if you measure it with some measurement operator and sub small m, then the outcome probability will be traced. Then basically associated with the outcome small n, you will get this matrix and sub m rho and dagger. Okay, so you think about this state, and so the probability of getting this small n outcome is just trace of this state, and that equal to trace of this state because trace is cyclic. And the post-measurement state is basically this state and normalized. And the normalization of density matrix is trace equal to 1. So you have this state divided by its trace. Okay, and finally you have the post-measurement, but special thing, I guess the extra thing about the density operator formalism is now we can talk about classical mixture of states. And so we can talk about classical mixture of a state that's just a post-measurement state. So you do a measurement, but you forgot the outcome. So you can have the post-measurement state of forgetting this outcome, and basically just this outcome probability times the outcome state summing together, and just summation m and this m rho m dagger state together. And so here are some example. So we have this example state rho here, and we do evolution with x, then you multiply x and x dagger before and after your density operator. And then you do measurement in z observable. You can measure the observable z, and we know observable z has a +1 outcome and state 1 0, and eigenstate 1 0, and eigenvalue -1 with eigenvector 0 1. Okay, so the probability of getting 1 is a trace of projectile 1 and rho, and this is 3 over 4. Probability of getting a -1 outcome is a trace of this projectile on 0, projectile on 1, and on rho, and this is 1 over 4. Okay, and then the post-measurement state, you do the calculation, and you should see that this is the 0 state, and post-measurement state of getting a -1 outcome is the eigenvector of 1. Okay, so those are density operator. This was in homework, and so this calculation should be familiar. Okay. And then we also have the reduced density operator. Okay, so this is wrong slide. And more about density operator, and and so we have this theorem saying that density matrix is a matrix is a valid density matrix if only if it satisfies two conditions. So first, rho has trace 1, so this is kind of like a probability of the matrix of the density operator. It is related to all the norm square of our state vector should be equal to 1. So trace of rho equal to 1. And second is that rho should be a positive semi-definite matrices. Okay. And then the density operator can also there are also different kinds of density operator, being mixed state or pure state. So pure state means that it's related to just one kth vector. Okay? And that happens when trace rho square equal to 1. And if a trace of rho square is less than 1, then it's a mixed state, means that it must be written as a classical probability mixture of different state. Okay? So this trace rho square equal to 1 means that it can be written as just one state here. Okay? And also different example of quantum state can give you the same density matrices. Okay? And then we go to this application of density matrix is we can talk about subsystem of entangled quantum system. Okay, so if you have an entangled quantum system on AB, then we can an entangled set of two system AB. then we can talk about the reducing density operator on system A. And this is everything you can learn on just acting on system A of this entangled quantum state. Okay? And this rho A is calculated by rho A equal to trace B AB, where trace B means partial trace and it is defined this way. Cool. So if you take a trace B on some tensor product of state, then you just trace the second matrix. So trace B of some A1, A2, B1, B2 equal to then trace B, then you will throw all the B part, so you become a A part matrix. So this is A1, A2, and then it's trace of this B1, B2, which is equal to B2 times B1. Because you do cyclic, so you put B2 together, so it's B2, B1, and this becomes a number. So this B2 times B1, so B2 bra times B1 ket, and A1 ket, A1 bra. And but this is only defined on some matrix on A tensor, some matrix on B. So if a more complicated matrix, then you can calculate by this linearity. Trace B rho AB sigma AB equal to trace B rho AB plus trace B sigma AB. This is a reduced density matrix. And then very quickly, we have two things that are related to reduced matrix. First is streaming decomposition. We say that any pure state psi between bipartite system AB can be written as psi equal to summation I lambda I IB. And here, the important thing here is that you only have one summation I. And the IA for every different I is also normal to each other, and the IB for each B is also normal to each other. Okay, and the lambdas are non-negative real numbers with summation lambda I squared equal to 1. Okay, and yeah. And the cool thing about this streaming decomposition is that those lambda set of lambda is unique. And the I and the IB are most of the time is unique. If you don't have lambda equal to each other, then they are unique. Otherwise, you can have some differentials in your I and IB state. Okay, and then we have the reverse of taking partial trace is purification, which is that if you have some density matrix A on system rho A, then you can always find another system R and find the pure state AR such that rho A equal to trace R AR. Okay. And here we give a constructive way to find this purification is rho A equal to you write rho A as its diagonalization, so rho A summation I lambda I then you write this AR equal to summation I square root lambda I IR. Okay. So this is a purification, and purification is not unique, but it's nice to know that purification exists. And I guess finally we have very close to end. We have a symptotic notation. So we have the big O, big omega, and big sigma notation. And big O notation basically means that so f of n equal to big O of g of n basically means that as n goes to infinity, f of n is kind of less equal to g of n. And big omega means that f of n is greater or equal to g of n. And big theta means that f of n is kind of between g of n, between the c1 and the c2 of g of n. Okay. Sorry, I've been going a bit quick. Any questions so far? And that's a symptotic notation. And in these few minutes, we give example of a quantum circuit. Okay. So two examples of quantum circuit. Then the first one is you go through a quantum circuit and you start with a computational base state and you get Bell state beta 00. This is an EPR pair. And what happens is you start with 00 and you go through Hadamard. Hadamard turns 0 to plus state, so this is 1 by square root to 0 plus 1. And then it's still 0 down here. And the C naught will add the first qubit to second qubit. So you have 1 by square root 2 and 0 still stays 0. And then this 1 0 will become 1 1. Okay, because you add this 1 to this 0. Okay. And here we have some other example. So if you have this weird circuit with C naught, and Z, and you input with some computational space is the ABC, Then you will add first A to B, so you start with A, B, C, and then go to first C9, it become, it is A to B, so it become A and B plus A and C. And then you add, you do another C naught, so you get add a second register to third register, so it become A and B plus A and C plus A plus B. And yeah, and finally you do Z gate on first qubit, and so you just have -1 to the first qubit. So you can write down in algebraic expression of what ABC will turn into at the end. It's just -1 to A, and B plus A, and C plus A plus B. Actually, just a computational basis stay with the phase. Because you don't have things too weird here. Okay. And finally we have these circuit calculation tips we have been talking about. So you can write down the state each time space in computational basis, and then you can apply the logical expressions such as ZA equal to -1 to AA, and C naught AB equal to AA plus B, and the Hedema turns 0 to plus, etc. And that's basically it. And you can also try to write down in matrices, in big matrices, but it can be very hard. Yeah. Okay. And so that's a quick review of what we talked about for the first half of this semester. So any question? Otherwise, we will have our midterm on Thursday. Okay. So I guess see you on Thursday.